All right, this lecture we're going to go back to the very beginning of the universe as extrapolated back from what we can guess. So nobody was actually there, but we can do our best reconstruction as possible, and it's pretty interesting what we think happened. And there are ways of testing some of these possibilities with what we see today, things that are consistent with today's observations. So you've stumbled on extraordinary concepts in physics being taught at Michigan Tech, but even if you didn't pay any money to me or anyone else, Michigan Tech, you're still welcome to watch these lectures. Why is that? Well, it's good advertising for Michigan Tech, supposing they don't actually watch this to correct all my mistakes. And I don't know, I just think it's good information is fun to disperse. So you won't get a degree unless you register, though. So information is free, but diplomas cost money. But you can see all these lectures online here if you can read that, or you can go to search on with Google or something for Starship Asterisk and Physics X, and you'll find it there. The beginning of the universe, hotly debated. Almost every culture on Earth has a universe creation myth, and so I guess modern Western society our creation myth might be called a myth because I just called it a myth. I like saying myth. But ours is based on a bunch of data, so like other societies we can feel superior. However, even 60 years ago, there was a debate as to whether there even was a very beginning of the universe. It was hypothesized by several prestigious scientists that the universe was in a steady state, that it always looked the same. It wasn't only the cosmological principle, which was covered otherwise in other lectures, but it was the perfect cosmological principle that was being suggested. Now, the universe does not evolve with time, so it doesn't matter when we are. It doesn't matter what things are. They're always going to look the same. So it's sort of like you're teaching third grade, and every year you get new third graders. So you wonder why these students aren't getting any older. That's sort of like the perfect cosmological principle of third grade. The students always remain pretty much the same. Whereas if you followed the students through, let's say you were a student's parent, they're in third grade, then fourth grade, then fifth grade, you might begin to notice after some time that they're changing. They're getting bigger, for one thing. So the cosmological principle says that everything is the same in all directions, but the perfect cosmological principle says that things are the same at all times. So the Big Bang theory, though, because there is a bang in the beginning of the universe, does not adhere to the steady state universe, does not adhere to the perfect cosmological principle. In the Big Bang theory, the universe undergoes dramatic changes in time, and we only happen to be living through one of these epochs. So the cosmological principle, as I said, is less specific than the perfect cosmological principle, and the same it looks for every location. Interestingly enough, now with what's called inflationary cosmology and there are times in the universe would undergo phases when it would look pretty much the same at times during those phases. But that's not the phase we're in now. We're in a phase where the universe is changing what it looks like pretty rapidly. So the earliest we can pick things up is at the Planck time. It's called the Planck epoch. Earlier than 10 to the minus 43 seconds, and we're going to, what 10 to the minus 43 seconds after what? So I'm a person who believes that we really can't go before that in any meaningful sense to say that there wasn't really anything that we are sure of that happened before 10 to the minus 43 seconds. There could have been a bouncing universe, there could have been a singularity, we don't know. Many textbooks will say, oh, it started in a singularity, but no one knows how the universe really started. We can only go so far back. For instance, you can only remember so far back as to when you were an infant. But you believe time existed before then, but you can't remember it. Well, with our physical theories, we can only go so far back, 10 to the minus 43 seconds. And before that, we really can't say what's going on. Our general relativity breaks down. We need some kind of quantum gravity. We need some other kind of things to measure that would tell us what goes on there. But if we take the linear extrapolation of galaxies and just push them all together naively, then you can say that all the galaxies were together at some point in time. And you can say, call that time 0. But we can only pick up, then consider as a toy model things exploding from time 0. And so we pick things up at 10 to the minus 43 seconds. So before the Planck epoch, general relativity, space-time breaks down, no one knows. Okay. Between 10 to the minus 43 seconds and 10 to the 35 seconds after some time which we'll call the Big Bang, the universe expands and cools. Now this isn't surprising because the universe is always expanding and cooling. Even today the universe is expanding and cooling. But it really expanded a lot and cooled a lot then. Now if you saw some other lectures, you might think, oh, there's some exploding thing going out, some golf ball, and the particles are flying out into empty space. But that's not what general relativity says. It's more like a balloon expanding, and the density of the balloon material is going down and cooling down. So early on, you have what's called a radiation epoch. So if you took all the things were very, very hot back then. So if you were to go there yourself and step out of your impervious spaceship, you would be vaporized into particles that would soon be moving relativistically and be indistinguishable from light. So it's called the radiation epoch, because even if you were to go back then with your common mass, you couldn't survive. Nuclei sometimes form back then, but not for very long, because the temperature is so high. Temperature is a measure of how fast things are smashing into each other. Things are smashing into each other at such high speeds that it's breaking the nuclei up. So you don't have nuclei forming for long, they just break up. So you can't say they're really nuclei there because they're only there for a very, 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 very small fraction of a second. So you just have really fast stuff moving around. That's the radiation epoch between 10 to the minus 43 seconds and 10 to the minus 35 seconds before interesting things happen. At 10 to the minus 35 seconds, common wisdom says there was probably what's called an inflationary epoch. So the weak nuclear force froze out, which we'll discuss what freezing out means, and the universe started expanding exponentially. Gravity in the universe became, during this brief period, repulsive. And the universe underwent what seemed to be a sort of a steady state where the perfect cosmological principle would hold for this very brief period of time. The universe became much, much larger during this time, much larger. Which is important because it solves things like the horizon problem. Eventually, the inflationary epoch ended toward this time, and we are no longer currently in that inflationary epoch. But we're in a much larger universe. Okay, so things continue to evolve as the universe expands. So it goes from 10 to the minus 10 to the minus 32 seconds. We'll just keep expanding and cooling out to 10 to the minus 6 seconds. The universe keeps cooling. So once the universe is out of its inflationary epoch, where some kind of dark energy dominated, we're back into a radiation dominant epoch. So again, if you were to put down common matter, it would break up. We're getting right to the edge of when nuclei are stable. Okay, so the universe keeps expanding. So it went from now temperatures aren't just high exponentials, they're getting to where we can even think about trying to create something like that in the lab. When we get out to 1 second, the temperature cools from 10 to the 13 kelvins to 10 to the 10 kelvins. Actually, that's still high for accelerators. However, what's interesting about that is that you begin to get protons and neutrons and electrons and positrons freezing out, which means that once they form, the collisions aren't so hard and so fast as to break them apart. So you can have protons and neutrons again. Hold out. Still, particles are moving near the speed of light, and you still cannot have nuclei even at 1 second. But we're getting close. Okay, so when you get out to 100 seconds, then finally, when nuclei form, when they bang together and form, and they bang into each other, things are moving slow enough, the universe is cool enough, so that these nuclei are now stable. It's called being frozen in. So they've frozen out, in fact. I used the wrong one. The nuclei freeze out of the universe, and you can now have nuclei. And you get nucleosynthesis. So you get lots of hydrogen. Helium forms at this time. Very small amounts of high energy form because you have bottlenecks in forming because things decay at 5 nucleons and 8 nucleons. So the universe, because of that, is mostly hydrogen and helium. So that our universe today is frozen out from that epoch and is still mostly hydrogen and helium. Okay, so the next thing, as you get down to 3,000 Kelvin, then you have what's called recombination, and then you can have protons here acquire electrons that go around. Previously, whenever a proton acquired an electron, it would bang into another proton with an electron, and it would free the electron, it wouldn't stay. Or it would be hit by light that was so energetic it would just knock the electron out. So at this time, 400,000 years, you have recombination. You have atoms forming, and when atoms form, the universe, photons can now fly free through the universe and won't just instantly bang into something. So the universe, I guess, suddenly becomes dark at that point. And that's where we see the microwave background coming to us from there. So between 400,000 years and 4 million years, you don't have enough time for stars to form, so it's called the dark ages. Finally, at 4 million years, stars begin to form. It's cool enough, and even from then, galaxies form. So it's now the light ages, and actually those stars are so energetic that they throw back out some very energetic light, which reionizes the universe to some level. So the universe keeps cooling as it expands, and today it's cooled from unimaginably hot to only 3.7 degrees Kelvin, which is really, really cold. It's not, so that's essentially close to 276, I guess, degrees Celsius. No. Okay. If it was 3 degrees Celsius, it would be 276 degrees Kelvin. Sorry, I got that backwards. So room temperature is around 290 degrees Kelvin. So if room temperature is 290 degrees Kelvin, imagine how cold 3.7 kelvins is. Really cold. So if you were to go, so that's why you can't go out and heat up your coffee with the microwaves out in space. It's just not energetic enough. Okay, so there's lots of background light in the universe. So this is background light, again, light from the first stars that's being seen. I think this is in the infrared. So it's not the gray stuff you're looking at, it's the stuff behind that, which is conveniently covered red. So here's a computer simulation of some of the first stars forming. So this is a lot of the gas that's falling in. It's not a very simple process to form stars. Yes, gravity pulls it in, but as gravity pulls it in, the gas itself heats up, and if it heats up, then it wants to move back out because it has more energy, has more velocity, it might have escape velocity. So you get different layers evolving, and you need sophisticated computer simulations to find the first stars forming. So then here you see in the early universe, you see images from the Hubble Space Telescope that show some of the very early galaxies in the universe, that groups of stars are coming together and forming galaxies. Here's a picture of our local universe. You can see there's all these, let's go to different colors, all these filaments. So our universe, you have to go to pretty large scales for it to be uniform. It's not uniform on the very close scales. There are things like the Coma cluster, which is a very big cluster, and the relatively nearby Virgo cluster. There's all these superclusters, which are clusters of galaxies. So there's lots of structure in our local universe that has only had time to form because you need time for gravity to accumulate things. So here's a cartoon of the universe expanding. Got to move fast. Here's another cartoon of the whole process where inflation is here all the way up to modern times here. Our universe is now currently thought to be mostly dark energy, and I will get to that in other lectures. 70% dark energy, about 25% dark matter, which is a form of matter, which I'll explain again in another lecture, which is different from our current. So of that, hydrogen and helium make up 4%, stars make up 0.5%, neutrinos are thought to be about 0.3%, and heavy elements, which we are mostly made out of, is 0.03%. So we're only a small minority of the universe. So to review, the universe has gone through radiation-dominated epoch, where things were moving too fast and everything was essentially like light. Currently, we're in the matter-dominated epoch, where things are dominated by matter, but we're quickly moving into a strange epoch where things are dominated by dark energy, again, which will be discussed in future lectures. This is the Hubble Deep Field, which shows us the distant universe, and here is the Hubble Ultra Deep Field, where people are studying these little galaxies, these faint little galaxies there, trying to determine the redshifts and trying to determine what they look like so we can have a better understanding for how galaxies formed, which we still don't know all the details because it's complicated, and how the universe came to be the way it is today. And with that, I will leave you to future lectures. I'll see you next time. Disperse. So you won't get a degree unless you register, though. So information is free, but diplomas cost money. But you can see all these lectures online here if you can read that, or you can go to search on with Google or something for Starship Asterisk and Physics X, and you'll find it there. The beginning of the universe, hotly debated. almost every culture on Earth has a universe creation myth. And so I guess modern Western society our creation myth might be called a myth because I just called it a myth. I like saying myth. But ours is actually there. But we can do our best reconstruction as possible, and it's pretty interesting what we think happened. And there are ways of testing some of these possibilities with what we see today, things that are consistent with today's observations. So you've stumbled on extraordinary concepts in physics being taught at Michigan Tech, but even if you didn't pay any money to me or anyone else, Michigan Tech, you're still welcome to watch these lectures. Why is that? Well, it's good advertising for Michigan Tech, supposing they don't actually watch this to correct all my mistakes. And I don't know, I just think it's good information is fun to discuss. All right, this lecture we're going to go back to the very beginning of the universe as extrapolated back from what we can guess. So nobody was